Welcome back, guys. This video is about partial fraction decomposition. In particular, we're going to work on an example that has a linear factor and an irreducible quadratic factor in the denominator. So this might be our potential problem. We see this. We don't have a basic rule for that. It's a quotient. It's a rational function. Got a polynomial over a polynomial. There's no basic rule for that. The next choice, if basic rules don't work, I always want to try u substitution next. Take the derivative of this. Derivative of the denominator is 3x squared plus 6x plus 16. Can I take 3x squared plus 6x plus 16 and multiply it by something to get this? Now the 16 and the 25, that makes it, there's a problem there. So no, u substitution won't work for this. So we're going to have to do something else. We're going to have to do partial fraction decomposition. So the first thing that we do anytime we're doing partial fraction decomposition is we factor the denominator completely. Actually, there's one other thing that we needed to check. Basic rules don't work, u sub doesn't work. Notice that the degree of the numerator is 2. That's the highest power of x in the numerator. And the degree of the denominator is 3. Since the degree of the numerator is less than the degree of the denominator, we're just going to go straight to partial fractions. If the degree of the numerator is greater than or equal to the degree of the denominator, we just got to do long division first, and then you'll do partial fractions for the remainder over the divisor at the end. But in this case, this works out. Degree of the numerator is less than the degree of the denominator. 2 is less than 3. So we're going to start by factoring our denominator completely. So I've got x cubed plus 3x squared plus 16x plus 48. Now notice I've got 4 terms in this polynomial. Now this does not always work, but many times when you have 4 terms in the denominator, when you have got 4 terms in a polynomial like this, many times this can be factored by a method that's called factoring by grouping. So we're going to use factoring by grouping here. Just because of the form, because I've got 4 terms. Now this may not work. We're going to see if it does. So I group the first 2 terms together, and I group the second 2 terms together, the last 2 terms together, and I factor out whatever these 2 guys have in common. I look at the x cubed and the 3x squared. The coefficients are just a 1 and a 3. The coefficients don't have anything in common. But the x cubed and the x squared have an x squared in common, so we're going to factor that out. And then we're going to be left with something. So we say x squared times what will give us an x cubed. X squared times x gives us x cubed. And then we say x squared times what gives us 3x squared. And I have a positive 3. Now our hope is that when we factor the second group, we're going to be left with an x plus 3 over there as well. So we can factor out the x plus 3 from this group and this group. We're not sure that that's going to happen though until we look over here. If I look at the 16x and the 48, I want to factor out something from both of them, but I need what's left over after I factor it out to be an x as my leading term. I need an x left over. So my only option on this is to factor out a 16. Because if I factor out a 16, then I've got an x left as my leading term in those parentheses. I have 16 times x gives me 16x. 16 times what gives me the 48? It's positive 3. And that's very nice, because now I look at this group and I say, what do the groups have in common? Well, the groups have the x plus 3 in common, so we can factor that out. And then we say to ourselves, x plus 3 times what gives us the first group? Well, x plus 3 times x squared gives us that. And x plus 3 times what gives us the second group? X plus 3 times a positive 16 gives us the second group. So that's factoring by grouping. If you don't remember how to do that, or if you possibly never learned it. Some algebra teachers don't even cover it. You can Google that. There are lots of videos about factoring by grouping out there. So this is our denominator factored completely. After you've factored the denominator completely, you should look at that x squared plus 16. Does it factor further? No, it doesn't. It's a sum of squares. Sums of squares don't factor. Then you're going to write down the partial fraction decomposition. So you're basically writing down the form of the PFD for this particular integrand. So we've got x squared plus 3x minus 25 all divided by x plus 3 times x squared plus 16. So I'm going to say this is equal to this over here. Since that's a linear factor, I'm going to have a constant over that linear factor there. And then since this is an irreducible quadratic factor, if I tried to factor it further, I'd get x plus 4i and x minus 4i, and I don't want any i's in my answer. So we're just going to we're not going to factor that because it doesn't factor in the real number system. We're going to leave that as an irreducible quadratic. Whenever you have an irreducible quadratic, you get a constant times x plus a constant in the numerator. We're there. All right. And now we just have to find a, b, and c. If I can find a, b, and c, I've got a rule for that for its antiderivative. If I split this into two pieces, I've got a rule for that. That's going to be a u sub, and I've got a rule for that. That's going to be an arctan. I just need to find the a, b, and c. So in order to find the a, b, and c, we write down the partial fraction decomposition, and then we multiply both sides by the LCD. And of course you simplify. And remember, the LCD is the original denominator every time. It doesn't matter if there are repeated factors or not, it's always this. Don't just start multiplying things together. Don't do that. It's always always the original denominator. So I've got that whole group times the original denominator. And then I've got this times the original denominator. And then this times the original denominator. Okay, and the x plus 3's reduce. X plus 3's reduce here. X squared plus 16 reduces there. X squared plus 16 reduces there. And I'm left with x squared plus 3x minus 25 equals a times x squared plus 16 plus bx plus c times x plus 3. Now at this point, when we were looking at other problems that involved only linear factors, whether repeated or not, we would choose an x value that would make one of these factors 0. Now this time we can't do that. For this is only 0 if x equals plus or minus 4i. And we don't want to use complex numbers here. So we're not going to set this one equal to 0. We're not going to use complex numbers to get our answer. But we do need to find a, b, and c somehow. Since we have an irreducible quadratic factor, one thing that we can do is set this factor, this linear factor, equal to 0, and use it to solve for a, because if x is equal to negative 3, this will be 0, and this will be gone, and then I'll just have a constant times a equals a constant. So I can set this one equal to 0 and solve for a, so we'll do that to start. So I've just got this one equation with 3 unknowns, and I've got to solve it for a, b, and c. So we start by doing that, just like we did before. This is 0 when x equals negative 3. So I've got negative 3 times negative 3 is positive 9. 3 times negative 3 is negative 9, and then I'm subtracting 25. So those guys undo each other, and we just have a negative 25 over there. And this equals a times negative 3 squared, which is 9, plus 16, that's 25. And then I've got this whole quantity times 0, so it's gone. So just have negative 25 equals 25a. That's very nice. Divide both sides by 25, and you get a equals negative 1. Very nice. All right. So now I just need to find b and c. Now I could let x equal plus or minus 4i, but I don't really want to do that. So we're going to try a different method. Here's the idea. In order to find b and c, first I'm going to distribute my a and this b plus c times x plus 3. I'm going to distribute through. And you've got first times first, outer times outer, inner times inner, and last times last. You're going to do all of that. So I've got ax squared plus 16a. Over here I've got bx times x is bx squared. Outer times outer is 3bx. Inner times inner is cx, and last times last is 3c. All right, and now we're going to do something a little unusual. We're going to, or what it feels a little bit unusual. We're going to group like terms in x. Now don't group the a's, the b's, and the c's together. A lot of students do that because they don't really understand what it is we're doing. What we're trying to do is we're trying to write this quadratic polynomial in x, on this side. We're trying to write it in the same form as the quadratic polynomial in x that we have over here. A, b, and c are just constants. So I want a constant times x squared plus a constant times x plus a constant over here is equal to this, 1x squared plus 3x minus 25. So we're going to group like terms in x. First thing we do is grab the x squared terms. I've got an ax squared and a bx squared. So that's a plus b times x squared. The next thing we do is we're going to grab the x terms. I've got a 3bx and a cx. So that's 3b plus c times x. And then I'm going to grab the constant terms and group those together. 16a and 3c are our constants. So this is a polynomial in x on this side, and this is a polynomial in x on this side. Whenever you have an irreducible quadratic, like we did, we had this x squared plus 16 in the denominator of the partial fraction, or in the denominator of the original expression after we factored it. Whenever you have an irreducible quadratic, you're going to do this. And this is going to allow you to come up with a system of equations. Now we had 3 unknowns. We were looking for a, b, and c. This is going to give us 3 equations and 3 unknowns. And I'd say, how on earth did we do that? Right now I've got 1 equation with 3 unknowns. Well, this is a fact that we're going to take advantage of in this next step. Polynomials are equal if and only if. That's what IFF means, if and only if. Mathematicians use that abbreviation. If and only if their coefficients are equal. So if I have x squared plus 5x plus 10 equals ax squared plus bx plus c, the only way that works is if the number in front of the x squared, which is 1, is equal to a. And the number in front of the x, which is 5, that has to be b. And the constant term, that has to be c. You've done this many times whenever you use the quadratic formula to solve an equation. You said A is 1, B is 5, C is 10, and then you use the formula from there, right? That's exactly what we're doing here, but it's not as simple as this. The coefficient on this side has to equal the coefficient on this side, but instead of just having an a over here, the coefficient of x squared on this side is an a plus b. So what I end up with is 3 equations and 3 unknowns. That fact is a little bit of an aside, a very important aside. Okay. The coefficient of x squared on this side has to equal the coefficient of x squared on this side. So a plus b must be 1. And the coefficient of x on this side, which is 3b plus c, it has to be equal to the coefficient of x on that side. So it has to be 3. And the constant term on this side, 16a plus 3c, has to be equal to the negative 25. So we end up with 3 equations and 3 unknowns. But because we had this one linear factor, x plus 3, we were able to set x equal to negative 3 and solve for a. So I've got 3 equations and 3 unknowns, but since I know that a is negative 1, I can reduce that to 2 equations and 2 unknowns. So I can substitute in a equals negative 1. So I've got a plus b equals 1, where a equals negative 1. And 3b plus c equals 3. Nothing I can substitute there. If a is negative 1, that's 16 times negative 1 plus 3c equals negative 25. All right. So I can use this one to solve for b. Add 1 to both sides and you get b equals 2. Now if b equals 2, I can use that here to solve for c. I can also use this one to solve for c. So I think what I'm going to do is I'm going to solve this one for c, and then once I find my b and my c, I'm going to substitute them in here and make sure it satisfies the third equation. B and c had better satisfy this equation, and this equation, otherwise it doesn't work. We made a mistake somewhere. So just to check, I've got negative 16 plus 3c equals negative 25. Add the 16 to both sides. Negative 25 plus 16 is negative 9. So c is negative 9 divided by 3, which is negative 3. All right, so if we've done everything correctly, b should be 2 and c should be negative 3, and a was negative 1. We did that earlier. Just to check, b is 2, c is negative 3. The question is that equal to 3? 3 times b plus c plus a negative 3. Is that equal to 3? 6 minus 3 equal to 3? Yep, sure is. So it checks out. So my b is 2, my c is negative 3, and earlier we said a was negative 1. Okay, let's see. Might say, oh my goodness, Miss Townsend, that was a lot. How did we do that? Okay, let's go over it again. We wrote down the partial fraction decomposition, and we multiplied by the LCD like we always do. And then this time, we only had one linear factor. So we set x equal to the value that would make that linear factor 0, negative 3, and we found out what a was. But we could not do the same thing to find b and c, so we had to do something else. This is what we did to find b and c. First we distributed, and then after we distributed, we collected like terms in x. So I've got something times x squared plus something times x plus something equals 1x squared plus 3x plus negative 25. These two polynomials are equal. Then, because of this fact, the only way that this polynomial could equal this polynomial is if the coefficient of x squared on this side equals the coefficient of x squared on this side. So because of this fact, I'm able to write down this system of equations. A plus b has to be 1, and 3b plus c, the coefficient of x, has to be equal to 3. And this constant term over here has to be equal to negative 25. That's the only way those two guys are equal. The only way this polynomial is equal to this one. is if these three equations are satisfied. So I have three equations and three unknowns. We collected like terms in x, then we set the coefficient of x squared on the left-hand side equal to the coefficient of x squared on the right-hand side. And we did the same for x. And the constant term. And then you can solve that system of equations however you like. And it turned out, because we already knew A, that it was easy to find B and C. We had a third equation. We used that to check our work to find B and C. Okay, we're still not done yet. I know this has been a long problem. Sorry guys, 20 minutes into the video and we're not done yet. But we're showing every step, and that's why. Okay, so I've solved for A, B, and C. I've got A, I've got B, and I've got C. Remember why we did this. All of this was so that I could evaluate this antiderivative, this one that I started with. So I found A, B, and C. That means that this is equal to this without the LCD there. I need to replace A with what it is, what I found it to be. I need to replace B with what I found it to be, and I need to replace C with what I found it to be. And then I'll anti-differentiate that instead of anti-differentiating this. And I've got rules for these guys over here. I can handle each of these pieces over here using the rules that we've discussed earlier in this section and in the very first section that we talked about in chapter 8. So let's go back. All right, our original integral. Is equal to the integral of a over x plus 3 plus bx plus c over x squared plus 16. And I've left a space for my a, my b, and my c. And you're going to substitute those a, b's, and c's. Substitute those values of your constant into the form of the partial fraction decomposition. A turned out to be -1, B happened to be 2, and C was -3. All right, that is a log. I've got to do a u sub and then I'll do a log. Now this I can't do as it stands, but if I separate it, if I call that 2x over x squared plus 16 plus -3 over x squared plus 16, I've got a rule for that and I've got a rule for that. So this is going to work out just fine. So I'm going to split this into 3 integrals. This one requires a u sub. I'm splitting this into 2 integrals. That's a 2x over x squared plus 16. That requires a u sub as well. And then I've got a -3 over that. I think I'm going to take my -3 out so it looks more like my rule. And we're there. All right. So I want to take the antiderivative of this and this and this, add them together, and I'm good to go. That's my answer. All right, so let's do the u sub here. On this one, u is equal to x plus 3. U is almost always your denominator. Du is 1 dx. So that's du. So we end up with -1 over u du. And the antiderivative of -1 over u du is negative natural log of the absolute value of u plus c. We're going to let the other guys take care of the plus c. And then we're going to back substitute. So I've got a u here, and I back substitute x plus 3. Okay. That's that one. Something similar here. U is the denominator. And du is 2x dx. And this time we happen to have that exact thing right there, du. So this is du over u. Or if you prefer, and I do prefer, I like to factor off that du to the right-hand side. It's 1 over u du. So we get natural log of the absolute value of u plus c. We'll let that guy take care of the c. And then don't forget to back substitute. U is x squared plus 16, so we're going to substitute that in. All right, next one. So this is x squared plus a squared, or a squared plus x squared. Remember that a is the constant. So a squared is 16. That means a is the square root of 16, which is 4. Okay. Now this is our arctangent rule. So I'm going to bring my 3 down. According to my rule, I get 1 over a arctan of x over a plus c. And then I can distribute that negative 3. This negative 3 over 1 times 1/4 is negative 3/4. And the arctan of x over 4 is still there. So that's our answer. That's one way to write it. We could also write it this way. X squared plus 16 is always positive. So I don't need absolute value bars around it, because the absolute value of a positive number is just the positive number. I wrote that one first because that had a negative, so I'm going to write that one second. So here's an alternate form of your answer. Now I've got log of something minus log of something else. Remember, we can use this rule. If I have log of a minus log of b, I can write that as log of a over b. So this one is my numerator, that's my a, and that's my denominator. So if you're checking your answer in the back of the book, you might see it written this way. The brackets may be overkill, but I feel better when they're there. Try to be very clear with the grouping symbols. All right, so that's an alternate form. Okay, that was a long one. Let's go back through. If you factor that denominator and you have an irreducible quadratic, we factored by grouping, then you still write the partial fraction decomposition down. Don't forget, with an irreducible quadratic, you get a constant times x plus a constant in the numerator. Then multiply by the LCD and you get this after you simplify. And because you had a linear factor, you can select the x value that would make that factor 0 to solve for this guy, solve for that a. So in x equals negative 3, this one is 0, so that whole piece is gone. And I just have a constant equals a times a constant. Turns out that those constants are negative 25 and 25. So we got a equals negative 1. So we're there. But that trick is not going to work for b and c. The only way to make x squared plus 16 equal to 0 is to let x equal plus or minus 4i. And I don't want to let x equal plus or minus 4i because I'm in calculus of a real variable. I'm not interested in complex numbers here. So we don't want to substitute in the complex numbers that would make that 0. So instead, this is what we do. We're going to use a system of equations to find a, b, and c. So after we multiply by the LCD, we distribute, we get this. We collect like terms in x. Group your x squareds together, your x terms together, and your constants together. Then the coefficient of x squared on this side has to equal the coefficient of x squared on this side. The coefficient of the x on this side, which is a 3, has to equal the coefficient of the x on this side. The constant on this side has to equal the constant on that side. And so you get 3 equations and 3 unknowns. Because of our linear factor, we already know the value of A, so we can solve these guys for B and C. Then, as always, we back substitute and anti-differentiate. This one's a log. If you had an irreducible quadratic, chances are, if both of these are not, they're non-zero, you're going to split it up. You're going to have that over your denominator, and that's going to be a u sub, and then the constant over the denominator is one of your inverse trig functions. And actually, it's a polynomial, so it's always going to be an arctan. So you're going to see a lot of u subs, arctans, and logs for expressions like this. We anti-differentiate, we get the answer. You can stop there for our class, but if you're checking an answer in the back of the book, or you're checking your answer against a solution produced by a computer algebra system, it might look like that. That's totally fine. It's equivalent.